Hey everyone, so today we're going to go over LeetCode question 94, which is binary tree in-order traversal. So the question is asking us, given the root of a binary tree, we want to return the in-order traversal of its nodes value. So if you don't know what in-order traversal is, it's probably better if we go over a couple of examples, but essentially we want to return, given a root, return all the values on the left subtree first, and then return the root value itself, and then return all the values on the right subtree. So in this example, in this tree, so we have a root of 1, and it has a right subtree that consists of 2 and 3. So if you notice here, 1 does not have a left subtree, so we don't return anything on the left subtree part of that. But the root obviously exists, so we return 1 first, and then we look down the right subtree. So the right subtree has 2 and 3. And remember, we're prioritizing first returning all values on the left subtree. So since 2 has a left node of 3, we return 3 first, and then we go back up and return 2. So it might be a little better if we go over an example here. So we'll get rid of this. This is from earlier. Okay. So let's make this tree a little bit more complicated. Let's get this right here, something like this, right? Then maybe a node right here, and then we'll go ahead and also there's a new functionality for Sketchboard that I found is pretty useful, which is the freehand. So all you gotta do is press F on your keyboard, and then you can kind of draw lines. So this is like not a very straight line, but if you want to draw a straight line, you can kind of there's a command for that. Let me delete this. You can press, so you're in freehand, press shift, and just kind of drag it over. So yeah, this is a pretty cool tool for drawing diagrams. Let me draw one here. All right, let's give some values to these so that we can kind of distinguish these trees. So let's call this 1, right? 1, 2, and let's call this 3, and finally let's call this 4 here, right? Okay, so we have this tree here. So given the root of 1, we want to return all the values on the left subtree first. So what we want to do is we want to start going down the left side of this tree. So now we look at this subtree here, which is 2, I'm trying to 2 and 3, right? Ooh, having some trouble. Okay, so we're looking at this subtree. Since 2 does not have a left subtree, we now return the root 2 as the first value. So the result, it's called result, is going to start off with 2, right? So we output this value successfully. Now we look at the right subtree. So the right subtree is 3, but it doesn't have a left subtree. So we output 3. And remember, we still need to check if it has a right subtree, which it doesn't, so we're done with this node. So we've successfully output this subtree here. Whoops, I keep on trying to drag this over here. Yeah, so this part is essentially, we've already seen that part of the tree, so we're good with that part. So now we go back up, and remember, we started looking down the left subtree of 1, and since we've output everything in a left subtree, we now simply just output the root 1 in this case, and we just keep going. So now we look down the right subtree, and similar logic, similar reasoning will lead you to just output 4 in this case. Yeah, so in this case, the output is 2, 3, 1, and 4. Okay, so you can kind of see, like, in this question, we are prioritizing, if you will, traversing down the left subtrees. So we want to output everything on the left side first, and then we output the root, and then we output everything on the right side, like kind of in that priority order, if you will. So let's take a look at how this fits into our question. And one quick thing, we can do this question in a recursive or the iterative fashion. Now the recursive solution is a little bit easier, actually much easier. So let's, for the purposes of this video, focus on the iterative solution. And in a future video, we can look into the recursive implementation. So I'm going to sketchboard. So let's say we have a tree with a root of 1 that only has a left child of 2, right? So remember, just by a definition of in-order traversal, we're showing all the nodes on the left subtree first, and then the root, and then the right subtree. So by that definition, we want to think, how can we travel down the left side of this tree, right? Because we need to traverse down, right? So let's use that as kind of a starting point and see if we can get somewhere with that, right? So let me perhaps move this here. I want to move this into 2 windows, actually. So here, oops, move this a little bit smaller so we can kind of move this over and then shrink this a little bit. All right, sweet. That's a little better. Move this down. All right, so I have some coding area here. So going back to this graph or this tree. So how do we traverse? We use this as to take notes. How do we traverse down the left left side of the tree? Right. So in order to do that, we can denote we need a node, right? Like we need a pointer to the current node, right? So let's say we had a current node variable here. Let me get rid of this. So what are we doing when we're traversing down the left side? So essentially, every time we see a current node, we want to set the current node to the left child of the current node, right? So in this case, current node is 1, and the left child of the current node is 2. So it's a very simply, we can just iterate down the left side by saying current node is current node dot left, right? So that's, in this simple example, we can get to 2 if current node is 1. We can get to 2 by setting, current node is a current node dot left, right? So this is just for one node, but what if we want to do this again and again? So we need some kind of loop. So what we can do is we can set while there's a current node, right? Because at some point, if you keep on traveling down this tree, current node is going to end up being empty or none in Python's case. So if we say you're at 2, say you set current node as current node.left again, then current node is going to be none. So I think that's your indicator that you want to break out of this loop. So what we can do is while current node exists, basically, right? And again, this is just semi-Python pseudocode, so we can fix the syntax later, right? So while current node exists, current node is current node.left. Okay, so that's very simple. That's if we had a longer tree here or a larger tree. Freehand, right? If this was the case, then this loop will allow us to travel all the way down until current node hits the left child of 3, which is none, right? In which case it'll break out of the loop. Okay, that's all fine and great, but for this question, we want to somehow, remember, we're visiting all the nodes on the left side, right? That's fine. We're traveling down the left side, and we have a pointer to the current node. But we still want to somehow be able to keep track of all the nodes that we've seen. So in this case, how do we keep track of that? Well, we could add it to a list somehow, but how do we want to add to a list? So for this question, remember, we're doing in-order traversal. So if we're doing in order traversal, let's say, in this case, we want to output all the left nodes first, right? So this output, what would it be? It would be, the result would be 3, 2, 1, right? So we're outputting 3 and then 2 and then 1. And you can kind of see that this output is outputting the nodes in the order that they were most recently visited, right? And so that might make you think, okay, so what data structure? Maybe we want to store it in a data structure that allows us to access these nodes in a most recently visited fashion. So how can we do that? Well, we can do that using a stack, right? So what if we, in this while loop, while we're visiting the left side of the tree, what if we just put these nodes into a stack, right? So let's say current stack.append current node, which is Python's way of pushing elements onto a stack, right? So now we're starting to get somewhere where we can keep track of the nodes that we visited, right? Okay, so let's just keep on going down this example, right? So let's just say, remember, we're still in brainstorming session here, so this isn't, obviously this code isn't ready yet, but hopefully as we brainstorm, we'll get an idea of how to actually code this out, right? So let's get rid of this tree or this node just to keep things simple, right? So let's say, okay, say we have this code and we've reached current node is none, right? So at this point, current node is none. I'll use this to represent it, right? So what do we do in this point? Because remember, we still want to output the nodes, right? We're not just traversing. We want to output like a result of the traversal. So in this case, we want to somehow access 2, right? And remember, at this point in the code, we've added the root of 1 and then the node of 2 into the stack. So in this case, 2 was the most recently visited node. So what we can do is, what if we popped off the stack and pushed that value into the results array? So what we can do here is, say we had a results list here. What we could do is results.append stack.pop. So let's keep this a little more simple, right? Let's go ahead and pop it off into a new variable. Say pop value, pop node, right? And then we want to take the value of this pop node and add it to the results list here, right? Okay, so this is all great, because at this point, stack is going to just consist of the 1 node, and results is going to consist of just 2, because we just popped that off the stack, right? Okay, that's all fine. So we're kind of taking care of 2 in this case, right? So you can kind of see like where, if you just think about this visually, right? So we're going down the left side of the tree, and then we hit nothing, right? An empty node. And in the spirit of in-order traversal, we want to pop off what we most recently saw, right? So there's nothing in a left child of 2, right? So we don't want to add it to the results list, right? But because in order traversal, you look at the root next, we can simply pop that off the stack and add that to the results, right? So what do we do after that, though? After that, we still need to check the right subtree of 2, the right child. In this case, there's nothing there, but assume there's something there. So let's draw something out. Let's call this 3, right? Okay, so assume this had a right subtree, right? So in this case, how do we handle this? So this is where it starts to get a bit interesting. And I've done this problem before recording this video, and this is where I kind of got stuck implementing this. But in this case, what if we just set current node equals the current node dot right, right? Or sorry, let's go ahead and because the pop node is 2, right? Let me write that down just to be really explicit. Pop node is 2. We want to set the current node. Let's set the current node to pop node, right? And then we set, which is 2, and then we set the current node to the right child of the current node, right? So this is where the question gets pretty interesting, because remember, we are setting, after we've added the value, the last pop value node into the results list, we automatically set current node is the current node dot right. So some people might ask, and this is something that I did previously, was why not check if the current node, the right child of the current node exists? Like, why can't we do something like this first, right? Like, why do we set it to, why do we just set it without any conditional? Because those will come out as none, right? So in this case, the pop value, the pop node was 2, so when we set it to the right child, current node is going to be none, right? So in this case, let's just do like a thought experiment. What if we actually, instead of doing this, we wrap this in the if condition? So if current node dot right is not none. Let's do it like this. Current node dot right. Okay. So, what happens in this case? Well, in this case, I forgot this part too. Current node is actually, we set to the pop node here. Yeah. So in this case, current node is 2. And we check if current node dot right is not equal to none. We only set it in the case that it actually exists. But in this case, once we hit this part of code, current node is still 2. So if we go back up here, we hit this part of the loop, which is while current node exists. So obviously current node, which is 2, still exists. So we're going to enter this part of the loop again. And you can see that this is going to start to cause problems, because we'll start to enter an infinite loop, because we've already checked this part. So a kind of trick to bypass that is to get rid of this conditional and immediately set current node is current node dot right, because then this is going to be none, which is going to then bypass this left side traversal check, and then continue on with the rest of the going back up the tree, if you will. Because remember, so we had at this point, all right, let's say current node is 2. Let's start from here. Just kind of refresh our memory. Current node is 2. Remember, the stack is 1 because we popped off 2, and results contains 2, right? So we go down here, current node is now none, right? And then we go back up here. So bypass this part, and then we do stack.pop. Remember, stack.pop only contains 1. So pop it off, stack is now empty, and then add to results, it's 2 and 1, right? So this allows us to go back up the tree and add all the other values, all the other nodes to the results. Otherwise, if we were to wrap this into conditional, which is when I first tried this problem, that's what I tried doing, and I had a lot of difficulty kind of, understanding why it was entering a loop and how to break out of it. But the simple solution is to basically remove that if conditional check. So now that we are at this point in the code, let's see what happens if we have a right child somewhere. So let's just add a right child to the node 3 here. Draw this out. Okay, awesome. So let's, I kind of cleared the comments here, but let's kind of revisit. So when we're at 2, at this point in the tree, so what do? We added results to 2. Yeah, what is current node? So current node is, okay, so we're at current node is 2, right? So current node is pointing to 2. So what I mean when I click on this is that current node is referring to this this node here, right? And then what does stack look like? That's another important data structure that we're keeping track of things. So stack is 1, right? Because we popped off 2 up here, okay? All right, so let's start off from this part of the code, right? So when we set current node as current node.write, remember we are essentially starting over with a new tree, right? And because we're at the end of the loop here, when we enter the top, we are doing the same thing earlier with 1 as we are with 3 here, right? So now current node is 3. Current node is 3. And we apply the same logic up here. So while current node exists, like you can imagine, in this case, there is no left subtree, but you can imagine if there were a left subtree, then the same logic would apply that we just visited with the root of 1 here. So in this case, let's see, while current node exists, current node is 3, so we have stack is 1 and 3, and then current node becomes none because 3 does not have a left child. And break out of this loop, and then pop node is stack.pop. So what we're doing now is pop node is 3, and we append it to the results. Let me just update this comment from the previous cycle of the loop. So 2 and 3, and then yeah, so we pop the stack up here. So yeah, this is correct. Stack is just 1 here, and then current node is the pop node, which is 3, and the current node is current node.write, which is none in this case, right? So we go back up the loop, and we don't traverse down. We bypass this left side traversal. We do stack.pop. Remember, stack down here is containing just 1. So pop node is 1, and then we add that pop node value to results. This is empty. We just popped it off, and we keep going down here while current node. So current node was, what do we pop off? 1 here, right? That's great. And then current node.write is none. Okay. And we go back up here. Okay, so we need some kind of condition on this outer loop, right? Because right now, remember, we hardcode this to be true just to kind of get into habit or get into the mindset of thinking of this in a loop fashion. So what if we remember? So the stack is to keep track of things of the nodes that we've seen previously. So it would make sense that once we run out of things to see, we break out of this loop. So let's add this conditional here. So while the stack is non-empty, we apply all this logic here. So, and as you can see here, from the example we just had, once we popped off 1 from the stack was empty. So once we do the check up here again, it'll break out, right? So in this case, we're pretty much code up the meat of the algorithm here. So at this point, we've broken out, we've done all our checks, we can just return the results, right? So we need to do some initialization up here. What do we need? A stack. We need a results, obviously, and we need to set current node to. It makes sense to set it to root first, right? And let me clean this up. It's not none while it exists. Okay. Oh, and one thing you might notice is that starting off, when this code first runs, the stack is going to be empty, right? So we need basically like a do while loop, or another way to do this is we can kind of, to bypass this, say while current node is not none, right? Because in this case, when we first run this code, current node is immediately set to root, and root is actually not sure. We might be given an empty root, in which case this will be fine because it will just return results, which is empty, which is what we want, as from the example here. But in the happy case that root is non-empty, we can add this check so to kind of force it to go into the meat of the algorithm, right? Let me change that to or. Yeah, and so this should, just from our going over the simple tree here, this should work. So let's try this. See if there are any bugs. Name cur. Okay, so it should be cur node actually. Try running that again. Oops, not in premium. Okay, awesome. Let's try to submit this. See if this submits. Awesome. So, yeah. As you guys can tell, this is a bit of a trickier solution to explain. I think it might help when you're practicing on your own to obviously go through, draw everything out, draw the tree nodes out, and comment in the code, like what the stack is, what the results list is, what the current node is at each step. I know a tree can be pretty complicated because it can branch off in different directions and such. But if you just keep a simple tree, even walking through that simple tree will help you a lot in understanding how to implement this. I think one of the bigger things as well is, at least for me when I was doing this question, is this current node is current node.write piece here in the logic. So definitely focus on this part. Really try to understand why we set this no matter what, no matter if current node.write is none, why we set this, like we kind of explained earlier. But I think it might be helpful if you guys kind of went through this on your own as well, and really focus on that part, because I think that's the key to understanding this question.